Hello everybody, today this will be a tutorial on how to do CAM in Fusion 360 at the Bechtel Center. So this video will be mainly for setup and the starting process of your part, and later videos will be more complicated in-depth Fusion tutorials. Everything in this video will be timestamped. You can see in the bottom there's chapters that you can skip to. Feel free to skip sections, rewatch sections, play back faster, whatever you need. So I'm going to start by going through some resources that we've made. So if we go to the Bechtel Center website, so BIDC Purdue, and then we can click on our website, and under resources on the side here, there will be some metalworking guides. So first you'll need to join the BIDC Fusion 360 team, and that is just so you get access to all of our tools, fixtures, and all the nice things we've made for you. And then there's the mill toolpath guide, mill tooling guide, lathe toolpath guide, work holding guide, and hopefully we'll make some more. Cole Sikorka is currently doing this, and thank you very much to him. So a lot of what is going to be in these videos is also going to be in these guides. We can see that there's in-depth guides with pictures and how to do everything you need to do. All right, one more place that you can look is Titans of CNC. So I'm going to be doing a tutorial on the Titan 9M today. And so Titan 9M, we can see that he has made tutorials to do CAD and CAM for this part in almost every single software, and he has a lot more under his academy. And then one more place that I like to look for guides is on YouTube. There is John Saunders over at NYC CNC. He has some good Fusion 360 tutorials, and this playlist is very nice. And then also most of the stuff that he puts out, he uses Fusion 360. He has good videos on how to do things. So feel free to go look at these three resources or anything else you find. All right, let's get into our actual part. Today, as I said, we'll be making the Titan 9M. It looks like this, and I'll be doing the CAM for this. I'm going to assume that you know how to do some CAD and that this has come across, but there'll also hopefully be some CAD videos. Okay, we can either make our CAM directly in this part and in this workspace, or what I like to do is I like to make a new file, title it our part name, and then CAM. This keeps my CAM and my CAD separate, and even though Fusion 360 has integrated CAD CAM, I like to have everything a little bit separated so I can go back and refer to my CAD when I need to and edit it there, and then I can have my CAM file a little bit separate. All right. To get started, we first need to import our file into our design, so I'm going to right-click the file and say Insert into Current Design. This will then take our part and place it onto our workspace. The origin of the part will be in some place that is not our current origin, so I think it matches origins. I'm not entirely sure what it does and how it places the part, but it's not currently where I want it. You can just leave the part where it is. For me, I like having everything centered around the origin because then when I click these buttons here, it goes to the correct place. So I will unground this from parent, and then I will joint this with either the joint button here, or I like to hit J for joint, and I can click on this little circle, this dot in the middle. Right now it's really hard to click on that dot, so if you press and hold Command on a Mac or Control on a Windows or Linux system, you can then just move it, and we can click on both points, and it moves nicely over. I'll hit OK here because this is where I want it to be, and I will hide my joints in my origin. So now our part is in our workspace exactly where it wants to be, and now I can start bringing in all of my fixtures and my stock model and everything that I need. Let's work on our stock. For our stock, this CNC machines are subtractive machines. So we start out with a big piece of stock, and our part is hiding within the stock, and then we cut away all of our stock until we get our part. So in order to find our stock, let's first find the minimum dimensions of the part. So let's measure the part by either using this measure tool with inspect or just hitting I. And I can see that if I click on this, I can't really find any points to snap to. I would like to measure the overall length, width, and height of this part. And currently I can measure the height by clicking on the bottom and then the top. And I see that is 0.75 inches. Okay, so my height's 0.75 inches, and then how do I find the length and width? So I can go back and I can hit I and then click this Show Snap Points button over here. This will then have a bunch of little points that I can then hold Command or Control and go and click on these points. And then I can see that my part is around 6 inches in length, and we can do the same for the height. Let's see, this part and this part look like they're the furthest. They might not actually be, but we're going to round up to 2 inches, so it's fine. Okay, so now I can go into my parameters, which is under modify, and then change parameters. Or for any shortcut, I can hit S and then type in what I want. So I typed in parameters for change parameters. I will add the 3 parameters, so stock X. We said that this one was 6 inches, stock Y, and we said that this one was 2 inches, and then stock Z. And then I'm going to say this one is actually going to be, let's say, 1.25 inches. I'll show you why I decided to have a dimension much over the 0.75 inches in a minute. It's to do with our tool clearance. All right, now let's model our stock. So I can then just make a new sketch on the plane that I want. I usually choose this one. I'll make a rectangle, and then I will dimension these. And for the parameters, you can just type in the parameters and they will automatically appear. Okay, and then when we extrude this, critically, I want to make this as an operation to be new component. This will make a new component over here on our design tree, and as you can see, it's called component 1, and this also lets me move this around. It is not grounded in place anywhere, and I can move it where I want. So I'm going to rename this to stock, and then I will also change the opacity to around 30%, so I know that this is stock. I'm going to show my Titan 9M, and I'm going to joint the top face of my part to the top face of this. All right, and then now our part is fully enclosed in our stock, but I will want to move this up by around like 100 thou, so 0.1 inches. 1 thou, by the way, is 0.001 inches, and it's kind of how machinists like to refer to their dimensions. Okay, this leaves us with a good amount of stock on our bottom. And since we're milling this away, we need some way to hold this. And usually what we hold things in is a vise. So a vise has 2 parallel edges, and we'll use that to clamp down on the bottom here. That'll let us take an end mill all the way around the part and remove all the material down to a certain line, and then we can decide to flip it over and face off the other side. All right, so now that we have our stock and our part, I'm gonna save. I save a lot, save early, saved often. Fusion currently crashes a lot. I hope they fix that pretty soon. Okay, now my part is set up and my stock is set up. We can go and grab our fixture. So I'm gonna go to the home, and then under here, we have work holding stocks and machines. If I open this and I scroll all the way down to tables, I can see that we have tables for each of our machines. So we have the VF2, the VF4 4-axis, and the VF4 plate. These correspond to physical machines that are in our shop. So we have a Haas VF2, we have 2 Haas VF4, one of them just has a plate in it, and one of them has a 4th axis, which is why they're named differently. I'm going to choose the VF2 as my machine that I want to use, and you will choose your machine based on availability and how you just like preference eventually. All right, so I right-click that, insert it into my current design, and then critically, I'm going to go here, right-click this, and break this link. I need to break this link because currently Fusion has said that this table here and this table here is the same thing. So anything that I update on the table in my design will be updated to the VF2 in this work holding stocks and machines folder. And since everyone in the center uses these folders, that will be a big problem. If everyone's editing these, then things will get messed up, and it's just very nice for everyone to have their own clean workspace starting out. All right, I like naming everything, so I'm gonna name this op1 fixture. And then we can then move our part into this vise. So from either reading the work holding guide or just knowing what I want to do, I'm going to hold this into the snap jaws of our Geppard 300s. This might change in the future. Vices, work holding, all of these change. Please refer to the website docs or just come in and talk to a peer mentor to know which vice and which work holding you should use. All right, so now I need to move this part into my vise. So I'm gonna, again, joint the bottom of my stock to this little, if you can see, there's this little sketch dot inside of the vise, and I can click on that and it'll move the part there, and I can just hit OK. So now, by the way, to zoom in and go home, you can just double click your middle mouse button. We can see that our vise or part is in our vise, but we're also clipping into the vise jaws. That doesn't actually work in real life, and we're trying to model real life because 2 pieces of matter can't occupy the same space. So what we're going to do is we're going to need to open this vise jaw a little bit. And what we've done is in our parameters tab, we can see that there's a whole bunch of new parameters. There's this parallel thickness, parallel height, jaw gap, and the jaw gap for all of these. Since I'm using the Gepard 300 short snaps, I can change the jaw gap here to just be my stock Y. And then this jaw has opened up and we have our part now fully enclosed in the jaws. All right, so this will be the setup for our first stop. It was that easy, that's all we need to do. And as we have new stock sizes, so let's say I go down to the stock room and I measure my stock, and it's actually 8 inches in X, I can then just change this number to 8, and my stock automatically updates. So that part is really nice. We can have our stock be the minimum dimension, so then we go down to the stock room, we know what size we want. All right, let's go back to why we've held it by why we've left a bunch of stock at the bottom. So as I said before, we're going to have a bunch of space that our end mill can go down and go past the bottom of our part and not worry about milling into our vise. Okay, so now that we're done with setup, at least for this operation, let's go over to CAM. To go over to our CAM workspace, I'm going to hide this data panel because we don't need it anymore. And then from design, I'm going to go over to manufacture. This is a new workspace. It looks a little bit different. Our top bar is different and our side is about the same. I'm going to again expand our model tree so I can see all of our parts. Okay, everything in CAM starts with a setup. We need to tell the machine, hey, where is your 0, 0, 0 point? Like, where do I reference all of my dimensions off of? Where is my part? What is my part? What is my fixture? What is my stock? All of these things, the machine has no idea what these are, so we need to go and tell it everything that it needs to know. So I am currently milling, so this milling tab is highlighted, and then I will click on setup, and we'll bring this dialog box up. Everything has turned yellow. It currently thinks everything needs to be milled, so let's define where all of our points are. I like to define our WCS first. So if our orientation, it looks correct, Y, looking into the machine this way, the Y is facing away from us, Z is facing up, and X is facing to the right-hand side. If this was wrong, you can change this model orientation to Z-axis plane and X-axis, and then choose a plane that is normal to the Z-axis, so I'll choose the top of this vise, and then a line that is along the X-axis. So let's take this one, and then you can flip each dimension as you need. But my model orientation was okay, so I'm going to go back and select model orientation. The origin is not going to be here. On all of our machines, we have set a 0, 0, 0 position to the top of this ball. So I'm going to say selected point, and I'm just going to click on the top of this ball. So now every single dimension that we tell our machine where it is, so let's say we tell the machine that this part is over here, it will reference this dimension over here. And this allows us to do some pretty fun things like probing our part directly from CAM. The machine knows about where our part is, and it can go and find our part with our touch probe automatically without needing us to jog the probe around and potentially breaking it. All right, now we can select our model. So I'll click this box and then I'll select the Titan 9M, which is our model. I would like to select it from the model tree and not just the body. That will make sure that as we change this Titan 9M, it'll update in CAM. And then for the fixture, I can then select op1 fixture, and we'll select all of this as our fixture. This is very important to do because it'll allow the simulation to know that, hey, my tool is currently inside my fixture and that is not good, and it will turn super red and it'll be very easy for us to go and see, oh, our tool is colliding with our fixture. This is another just safety check to make sure we're not milling into anything we don't want to mill. All right, and then under stock, we need to define what our stock is. Currently, you can see this yellow box around our part. This is saying that that is all the stock is. But we have this ton of space down at the bottom that is also our stock. So instead of relative size box, I'm going to go from solid and then just select my stock solid. And that'll ensure that as we update our stock and as we do things, the CAM software will know to then update our toolpaths to select all of the stock, to remove all the stock that it needs to remove. All right, and then in the last tab under post process, you can give it a name and number and comment if you would like. But what you do need to do for our mills is you need to change this WCS offset from 0 to 1. They're both the same. The 1 allows us to use multiple WCS offsets, which WCS stands for work coordinate system. So that's like a 0, 0, 0 position that our machine knows. And we'll say that, hey, the second one that we've set onto the top of the ball, you can reference that in order to set our first one. All right, so another thing that I would like to point out is what we did is we went from one tab, we filled out our tab, and then went to the next tab, filled out that tab, and then went to the final tab and filled that out. That's how almost everything works in Fusion 360. They've set everything out in a nice and logical flow to where you can just go through each tab, change what you need, and then hit OK. All right, this has created our new setup. So this is titled Setup 1. I'm just going to change the name to Op1, and then I'm going to save. All right, now we can start putting our toolpaths in. Now that we've put our setup in and we know exactly what we need to cut away and what we don't want to cut, we can start putting in our operations. So I'm going to go over here, I right-clicked op1, I'm going to go to create from template and then select XYZ probing. This is necessary because our machine currently doesn't know exactly where our part is. It knows roughly where our part is because we selected the top of our ball as our WCS home, but it needs to go and find exactly where our part is so it doesn't cut what it doesn't need to cut and it doesn't cut too much. So we're going to double click our Z probing, and since this is from a template, all of this here is already set, and all we need to do is select the surface that we want to probe. So we can probe two different surfaces. We can probe the top of this, and as you can see, all these arrows is where this probe is going to touch. Since this is Z probing, we want to touch off on the Z surface only. Or we can probe off the vice jaws. So which one do you do? Do you go, and if I click on simulate, let this load, do we go and probe off of the top of the stock, or do we go and probe off the vice jaws? This question will have to be answered based on your specific use case. I would probe off of the vice jaws when you are scared of milling into them. If you probe off of the vice jaws, there is no way that your tool is ever going to go into your vice jaws unless you've programmed that in CAM. However, if you're probing off the top of your stock and your stock is shorter than you actually think it is, the toolpaths will then be shifted down based on where your stock actually is in real life, and you could mill into the jaws. Since over here, I think we have plenty of clearance. Our stock size, I'm not concerned about measuring, as my measurement error isn't going to be in like a ton. It's not going to be over our 2.82 inches. I'm good with probing off the top of our stock, as long as I make sure to update my stock to whatever it is in CAM. So I'm going to probe off the top of my stock, and then I'm again going to probe off of the part in XYZ, and this looks good. I will also change my over travel to 0.5 inches. That's going to say that, hey, I know that my CAM software has said to stop at this point here, but I'm actually going to go a little bit further to make sure that I actually touch the part. And that will allow you to put the part in slightly the wrong position and be okay. All right, so now I've done my probing. Now my machine knows where the part is. Okay, now we can start actually removing material. And at this point, we don't need our stock, we can just hide it. Let's go, and we're going to see that we have a bunch of stock that's above our part. So if I can make the stock transparent, we can see that we have a good 0.1 inches as we've set above the top of our part. We're going to want to face that off, and the fastest way to remove that material is with this face operation. It's just going to go and take a big cutter and move it across the top of our stock. So we have a bunch of tool libraries here. A lot of these will change, and they'll change fairly soon. But for now, we can look at our machine. So the VF2 and the VF4, so we're using the VF2, so we're going to want to stick to mostly this library. I can select face mill, and we have the 2-inch Stelrum. This is just a big face mill that can remove a bunch of material off the face of a part very quickly. So we're going to select this tool, and then now we're going to go through the tabs as I said.
This is just going to be a quick little addendum. Those tool libraries have changed. So now they are by machine. So as you can see, we have all of our BIDC machines. In the metal shop, we have the ST20, which is our 2-axis lathe, and then the ST20Y for live and static. That's our 3-axis lathe with 4th axis capabilities. And then we have the 5-axis, which is a UMC 500, and the VF2 and the VF4 plate mill, and then the VF4 4-axis. So for which machine you're going to use, you're also going to choose a tool library to that. Since we're using the VF2 and the VF4, I'm going to click on this. So to get your different tools, as you can see, there's a lot of different types of tools here. There's drills, there's end mills, there's face mills, there's everything in here. So to choose the right tool that you want, we're going to just use the filters. So we're milling, I'm going to find a face mill, so we're going to go face mill, and then this is the 2-inch Stelrum. If you wanted drills, you'd go hole making and then drill. If you wanted to filter between our high-speed steel and carbide drills, down here under material, you can choose HSS for high-speed steel and carbide for carbide. It doesn't matter if you don't know what these means, they'll make sense soon. And then for the heat shrinks, I just turn all the filters off and scroll down to the bottom. And we see that tool 9, 10 through 18 are all populated. All right, that'll be it for the addendum. Thank you.
things. And this is N1 raw aluminum, N2 low silicon aluminum or magnesium. What does all of this mean? So when you're making a part, you're making it out of a certain material. And in this case, this part that I'm making is aluminum. So within aluminums, there's a lot of different hardnesses of aluminum. So I can then go to our Discord. So the Bechtel Center has a Discord, and under links and resources, at the very top, you can see this material ISO grades. We're going to want to click on this, and it's a PDF that Kennametal, our tooling sponsor, publishes about which material is which. So at the top, we have all these letters. So P is for steels, N is for non-ferrous, and all of these, like P, M, and S, all of these correspond to a group of material, and then within that material group there are designations. So P0 is low carbon steels, and they usually go harder as you go down the list. So P6 is fairly hard. Okay, I know that we're running aluminum, which is non-ferrous, so I'm going to go down to the N section, and under here we can see that we have some material numbers. I'm running with 6061 aluminum, which is mostly what we have in our stockroom, or 7075. And as you can see, both of these are underneath N2, low silicon aluminum alloy, low silicon aluminum and magnesium alloys. Okay, so now that I know that it is N2, those are all the designations that I'm going to be using for all of our tools. Also, at the bottom of this, you can see that there's many more pages that go a lot further into what these materials are, and you can decide, if you have a more exotic material, what designation we want. One more thing that I'd like to note is we like running our tools slow and just taking it safe. Since we're doing mostly one-off parts, there's no need to run fast. Most of our time is taken into setup. So as you can see, P3 and P4, if I was using 4140 steel, it falls under both of these. P4 will be for the harder types of steels, so it'll be running slower. So if my material falls into two categories, I'm going to choose a bigger number that runs slower. So for 4140, I'm going to choose P4 and not P3. Going back to our cam, now that we know how to find our feeds and speeds, we can see that I've already chosen this N2 low silicon aluminum, and we're good. Okay, now that we've faced our part, what we've essentially done is made a bigger rectangle into a smaller rectangle. Now let's start cutting our actual part out of our stock. All right, so to do this, I'm gonna first want to go and profile the whole outside of my part, and then I can start working on the little details inside of the part. I have chosen to use an end mill to run around the outside of my part to remove all the material, and if you don't know which tool to use, you can always refer to our mill tooling guide, or you can come in and ask a TA and ask for help. All right, so to remove all of our material, I'm going to use this 2D adaptive clearing strategy. And for Fusion, if you hover over anything, it'll pop up with a little tooltip and tell you what it does. So this says it creates a roughing operation that uses a more optimized toolpath that avoids abrupt direction changes. I want to use this because it'll obey how much material that I'm telling it to remove, and it won't violate that. Okay, in our machines, we have some tools in heat shrinks. So these are holders that just live inside the machine, and our common tools live in there. So under all of this, these are the tools that we have for offer. I'm going to use a Maximate because, as we can see, this works with our low silicon aluminum, our N2 material grade. If I click on something like the Harvey, this is meant for steels and non-ferrous alloys. So as we can see, none of these have the N symbol, so we can't use this on aluminum. The Kennametal does not make these tools for aluminum, and they make specific tools for specific purposes. So I'm going to choose this Maximate and select our N2 low silicon aluminum alloys, and I'm going to click select. So this is our tool. This tab is done. Again, we have no multi-axis, and this time under geometry, it tells us, hey, you need to tell me what I need to cut. So I'm going to say, I want to cut outside of this and inside of our stock. So I clicked on this bottom contour, and we can see that it has highlighted that whole line, and all this blue section is what it's going to cut. I like that, so now I can keep going under heights. From the top height, now, since we've faced off the top, I can start from our model top, and the bottom height is selected contour. The selected contour is this blue line down here that I selected, but I'm going to say that, hey, I want to go a little bit further down past the part, so when I flip the part over for my second operation, I don't actually need to do the work of removing material and trying to line everything up correctly. So I'm going to say lowest of selected, and then model bottom, I'm going to go down around, there was 0.282 inches above the top of the vise. Let's say I'll go down 0.2 inches past the bottom. Nope, sorry, .075, 75 thou past the bottom of the part. Sorry, my bad. And we can see this blue line is past the bottom just a little bit, but still well above our vise, and that's what we want. Okay, under passes, I can see that our optimal load is 0.05. That's 10% of the tool diameter. That's great. All of this will hopefully be preset for you, and then our stock to leave, let's set this back to, okay. Our stock to leave, we have radial and axial stock to leave. If I hover over this, it'll show you that radial is on the walls and axial is on the floors. So since we're not doing anything with the floors, I don't need stock to leave. I'm just going down past the bottom of my part, but then radial stock to leave, I can leave this at the 20 thou. And since this is a roughing operation, it's going to create rough walls that I can go and then clean up with a finishing operation after. And I'm going to check the smoothing and feed optimization. Feel free to read what these do. Basically, smoothing turns a bunch of little line segments into arcs, since our machines can follow an arc, and then feed optimization will slow down in corners. Okay, there's nothing I need to do under linking, and I can hit OK. So as we can see, this has created our toolpath, and it will come around and remove all that material. I'm also going to make our stock non-transparent because I like to know exactly what is there. All right, now that we have our toolpath, I'm going to just double check a couple things. So each one of our tools has a flute length. If I go back to our mill toolpath guide, we can see that the flutes are these things highlighted in red lines. There is a maximum depth that you can cut based on these tools, and that's the flute length. So if we go back to our Fusion 360, we can click on our tool library and click on our tool. So as we can see, the flute length for this is 1.25 inches. We do not want to mill past 1.25 inches, or we will rub the shank on our tool, creating bad surface finish and potentially breaking the tool. So how do we make sure that we're not milling past 1.25 inches? I'm going to say that I'm going to measure my part, which we've already done before and we know is 0.75 inches, but I'm just going to measure it again to make sure. Wow, everything's stuck. Okay, great. So we can see that this is 0.75 inches and we're going down 75 thou past that. So 0.75 plus 0.075 is less than 1.25. So we are good and we can do that. Also, at the center, we have another rule just for running the tools a little bit slower. We're not going to want to cut down past 90% of the tool length in one go. You can cut 90% of the tool length and then you can cut the other 10% right after. I would recommend just splitting it 50-50 if you are doing it that way, since it's the same amount of time and just less pressure. But we can't cut past the bottom of the tool, so we can't cut past 0.125 inches with this tool, and we can't cut past 1.125, which is 90% of the tool length, or the flute length, at once. We are not violating either of these rules, so we are good. All right, so now that we've roughed the outside, we can watch anything with the simulate. I'm just going to speed this up fairly quick. This looks good. It's roughing our toolpath, it's roughing our part, and we're making good progress. And then now we can then go and start roughing everything else. I like to rough everything and then finish everything and not mix that up. Sorry about that, I'm back. My Fusion was acting up and it wasn't looking great. So we've roughed the outside of our part and now we need to start roughing the inside. I like to rough everything and then finish everything because as we remove material, our metal will warp and bend as the stresses get released inside of it. To rough the inside of this hole, there's a couple things that we can do. One, we can just do the same 2D adaptive thing again. I can go under geometry. Our tool is already selected since it's the last tool that we used. I can go under geometry. I can select the pocket. I can say we're going to go down to the lowest of selected, our model bottom, negative 0.075, and then from the stock top. All of this looks good. And then all of this also looks good, and I can click OK. And what we're going to see is there's this red spiral that goes down, and then it goes and roughs our part. So the red spiral is our helix. Since this is an end mill and not a drill, it can't just go directly through our aluminum. That would break the tool. These aren't drills, so it's going to go down in this helix motion and then cut the whole thing. I'm going to say that I don't like this because one, helixes are really slow. You have to run at a lower feed rate, and two, it wears out the tool. Since it's just cutting on the tip, it wears it out unevenly, and they're not great for chip evacuation. So the chips will sometimes get stuck in this hole. What I'm going to say is we're going to delete this, and I'm going to drill this hole out first. So I'm going to go under drilling, I'm going to select And then currently our drills for the VF series are going to be in Bechtel Go drills for VF. Eventually they're going to be moved into this VF2 and VF4 library. But I just need a drill that's larger than 1/2 inch. So I'm going to just pick this biggest Go drill. The Go drills are carbide, and then I can go under here and select the feeds and speeds that I need. As you can see, there's 2 N2s, flood or through tool. So these drills have holes all the way down the length. It's really cool. That can send coolant straight through the drill and into the tip. The machine, however, needs to be enabled for that option. Currently the only machines that are enabled for that are the UMC 500, which is the 5-axis, and the VF4, the 4-axis version. Since we're on the VF2, we don't have this through tool option, so we have to select flood. So I'm going to select that. And then under geometry, I can click the whole face, and that'll put it in the middle. But as you can see, the heights are all wrong. So we can go under heights, and we can say the top height is going to be the highest selected, and the model top and bottom height, lowest of selected. And this time I'm going to click stock bottom, not fixture bottom, stock bottom. And what that's going to do is that's going to drill all the way down through our stock. This will allow us to probe that hole that we've drilled from the first operation and know where our part is from a feature on the first operation. And that'll just make the probing more accurate and make our part a lot better. So I'm going to drill the tip through the bottom since the drill tips are angled, and I'm going to say just break through by 0.075 inches again. This breakthrough has to be positive. So now we can see that this drill goes all the way through our stock. And under drilling, I'm going to want to make sure the cycle drilling rapid out is enabled. With the Go drills, we do not want to peck. That wears the drill out prematurely, and our feeds and speeds for the Go drills are very good. So we can select that, and as you can see, we have a hole straight through the part. Now we can do what we did before. So we can go under adaptive clearing. I can select this little pocket, and then this will be with the same tool that we've been using, so our 1/2 inch maximum with our N2 preset. And then we can go under, make sure everything's selected correctly, and then under this linking tab, pre-drill positions, I will select this hole, this diameter, because that's where we've put our hole in. And then now when I click OK, we can see, and if we simulate, I can simulate this, and we have this drill going straight through our part. And then our end mill dropping down into the hole that's already been drilled and going outwards. This will be a little bit worse for chip evacuation, but this will be a lot better for the rest of the tool. Alrighty. Now that we've done that, you can see that our whole thing is just rough, finish. So I'm going to go through and quickly do the rest. Now we see that our inside bore is done. Now we need to rough and finish these sloped walls. So a 2D operation will not work for this because our 2D operation does not take into account the slopes. So what we're going to do is we're going to go under this 3D adaptive clearing, and we have the same tool. And then 3D operations are great because they kind of just do everything for us. So I'm just going to go and I'm going to click OK and see what happens. As we can see, it has done some machining, and most of that machining looks to be okay. I'm going to watch this. So I don't like this toolpath for a couple of reasons. I'll illustrate the main reason. So as it goes down into the middle, and then it starts going out into the outsides. At this point, it's done all of the stuff in the middle, and then it's going to go out and come around the outsides and cut inwards. What this is going to do is it's going to make little pieces of stock, which for this is fine. These are so short and so small that it won't hurt much. But on a longer part, these little ribs that it leaves can get quite bad since there's a long, thin bit. It'll sound really bad. It'll break off and fly across the machine, and that's not great. For now, I can just leave it. But what I am going to do is I'm going to show you how to fix that. So I can exit this simulation, and we found out that the reason that I didn't like this toolpath was because it was doing this outside bit after this inside bit. To do that, we need to give it a new definition for where it can go. And to do that, I'm going to create a new sketch. So I'm going to hide everything just because it's getting kind of annoying, and click on the new sketch button and then select here. And then I can project my curves that I want to show. So I can either go and type in S for project, or I can just hit P for project, and then I can select these two faces for the lines that I want. the reason why I selected those two faces is that's what's there before it starts sloping upwards. And then what I can do is I can go and finish these curves here and here. So now you can see that we have a full selection here. And what I'm going to do just to make it easier to select is create a new surface with patch. And then I can go like this and go like this. And then now this is going to create two bodies. So if I hide this, we have two bodies of a surface that I can say, hey, you can go and machine. All right, now I can go back to our manufacturer tab. I can create a new 3D adaptive clearing, and I can say, all right, the geometry that I want you to remove is just going to be everything that is on, sorry, let's hide this, on this side of this line. I can click on that. So I want it to be on this side. So I'm going to click this arrow, and then I'm going to do the same thing on the other side. So now if I hit OK, what I can see what this did is this is going to remove only what is on this side of this line, and I can take this and move this up, and then this is going to need to be regenerated. I'm going to click right click and then generate. And then now if we can see this, this comes from the outside in and it removes all of the stock like that. All right, it's going to do that to both sides. And now once this new toolpath comes in, if I simulate this, it's not going to have any of the weird, bits that get super thin. So I like this toolpath a lot better. What I don't like is this green here shows that this is a finished surface, so that's all the way down to our part. I can go and edit this under passes. I can say stock to leave. I'm going to just reset this to system default. And it's going to leave the correct amount of stock. And then the same thing here. Let's see. Okay, these are good. So now that looks good. Nothing's green. Everything's still rough. The next thing is we can see that we have a bunch of huge steps in the bottom of this part. Since we're going to then come in with a ball mill and clean these up, we're going to want to make sure that our steps are as small as possible. So I'm going to go over here, and under our passes tab, there's going to be our fine step down. This fine step down is a little bit too big for my liking. I'm going to set this to like 25 thou. This is going to take a lot longer, but what this is going to do is make sure that we don't need to do a pre-finishing toolpath, and I'm also going to reduce the stock to leave. And I will reduce the stock to leave on the operation before, so that it doesn't go and cut a bunch of air for no reason. All right, this is going to need to be regenerated likely again, because 3D adaptives, they can see what stock is left, and they can go and edit that before. Also, this error, ignore stock less than decreased to match the corner radius. I'm just going to remove that error, and the corner radius of the tool is edit expression. So tool corner radius. Okay. Now that error is going to go away, and everything will be nice and green. You don't necessarily need to remove every warning. Some warnings you do need to remove, and that's just based on what the warning is. As you machine parts, you'll get a better hang of that. So our part is mostly roughed. All we need to do now is just drill these holes, and then we can start working on finishing. So that is very similar to this thing. We're going to drill the holes and then come down with an end mill to make our counterbore. So I'm going to quickly go and do that. Now that we're done with our roughing, we can move on to our finishing. To do this, we first just need to remove, we have a little bit of material left on all of our surfaces. So, and right now we have our 1/4 inch Maximate inside the tool holder. So let's just finish the inside of these pockets because the tool's already in the spindle. Since it's a cylinder, I decided that I wanted to use a bore operation, and I'm just going to select all these bores. And then I can tell that this toolpath isn't going to go, where did my part go? This toolpath isn't going to go to the top of the hole because of this chamfer. Since this hole starts a little bit below, we're going to need to extend it manually a little bit higher. So I'm just going to extend it 25 thou past the top, and that should solve our issue. Now we can see it's coming out of our hole and going a little bit above. Okay, now let's do the outside and the inside and the flats, everything that's easy, and then we can go and do the hard things, which are these little pockets and the sand. All right, we will move back to our 1/2 inch end mill and finish the bottoms. So I can select our end mill. And then the geometry that I want to cut, this is a 2D contour, by the way. I can select the outside of this, and then under heights, I want it to go past the bottom, and I'll say 70 thou past the bottom, even though we did 75 thou before, since we only want to cut on either the side or the bottom of the tool when we're finishing. That'll have us less tool pressure, and the tool will bounce less, leading to better surface finishes. So I can hit OK on this. And also, if we want the best surface finish, we can also go to N2 slotting. It'll move our tool slower and give us a better surface finish. And then now let's do the inside bores. So I'm going to select a bore again, and then since there's the same chamfer, I'll go 25 thou past the top, and then make sure that this is on the slotting feeds and speeds. Great, and then I can do one more on the inside and go 70 thou past the bottom of the part. And then finally, we just need to do these faces. There's a 3D operation called flat, which will look at our model and find all the flat faces. And now what I need to tell it to do is I need to tell it to not cut this face. So I'm going to make a new selection, click on avoid surface, click on my face, and then hit OK. And then now this looks good. The step over here, I'm going to change this to R50 thou again, and then machine over holes and cut interior both ways. And this will then make a flat operation that goes past all these edges and only cuts the flat parts. I can also see that it's cutting this face and this face inside, so let's add that to the avoidance group and tell it to not cut those. Let's open this. Oh wow, I can't select on this. Okay, this face, and this face. Okay, that'll make sure our floor finishes are consistent with everything, and we're not having a flat end mill finish the bottom and then ball mill finish over the same area. That'll just look weird. All right, that's all the easy stuff taken care of. We can watch this simulation and we can make sure that we've gotten everything. All right, looks like everything that we want to be green is green. And then now we just finish these sections here. To do that, I'm going to find the minimum radius, and I'm also going to turn off the fixture, not the part, the fixture, because it's getting in the way and I'm clicking on it when I don't want to. So I'm going to click on this and it's not telling me the radius. So I clicked on this and it's telling me that the radius is 0.25 inches. That corresponds to a 1/2 inch diameter cutter. I do not want to use a 1/2 inch diameter cutter in this case, because when the 1/2 inch cutter comes into this radius, it's going to be a lot of tool engagement and it's going to want to bounce because it started to cut a lot of tools. I'll put a link to a video in the description of someone who talks about this a lot more in depth, but for now, let's just take it that we're not going to use a 1/2 inch end mill and we're going to use the next smallest size down, which is a 3/8 ball. There's many ways to do the inside of this surface. I think in his video, Titan recommends to use a scallop and to go inside, but you can decide and play with it to your heart's content. I'm going to try the geodesic, which uses a scallop or a blend as its toolpath, and then it generates based on that, but it's a lot easier because the containment boundaries are already selected for you. So I'm going to go through and I see I have a 3/8 dual lock ball maximate. I will select this tool and I see that the speed is way too high. I'm going to lower this to 120, and I will likely fix this before you guys get a chance to use this tool. So you won't have to worry about that. All right, this geodesic is asking me for drive surfaces, so I'm just going to click on all the faces that I want it to cut. Now that we've selected all of our faces, the type of passes under here, we have a choice between scallop and blend. I'm going to just leave it as scallop for now. Let's go, everything's automatic. And then we're going to see, I'm going to spiral, remove cusps at junction. And then the maximum step over, I'm going to say 10 thou to make it a very nice surface finish. I'm going to hit OK. Drive surfaces should comprise of exactly one connected region. What this is telling me is that I've selected too much stuff. I'm going to first watch this and then mirror it over just to see if this is what I like. And it looks like a fairly good toolpath, I will say. Let's slow this down. And then where is our tool? Great, so it's coming in from the top and it's working its way down. That looks great. That looks like it'll work. And then we can duplicate this. We have both sides getting finished. And then now the last thing we need to do is this top bit, and then we just need to do our chamfers. I think a flow will work nicely on this. So then we can again just select our curves. Same tool, same everything. We can say our step over is going to be 10 thou again, and I'll hit OK, and then we'll see what this looks like. This looks good to me. So let's watch this. All right, I don't like one thing, and we can fix that fairly easily. It's bouncing around instead of just finishing up one side and then finishing up the other side. All right, now that we're done with finishing, everything is green on our part, everything looks good. We can then work on deburring. I've gone and I've removed those modeled chamfers, and we can then now go and deburr our part. We deburr our part because we need to break all the edges so they don't cut anyone. These edges will be sharp and it also looks nice, but mainly they're just very sharp. I like the deburr toolpath. A lot of people don't. I don't know why. I really like it. And then the deburring tool that we're going to use is our dual lock chamfer mill. And this is just a big 1/2 inch chamfer tool. It works in most cases. And we're gonna go N1 through N6 non-ferrous. That's our material grade. Geometry, we don't need to select anything. The thing that we need to change is cut on fixed point on tool. I'm going to change that to 15% so it doesn't cut like at 1/2 inch down the tool. That would be fine, but you're usually able to get for more places if you're just cutting with closer to the tip. And the edge radius looked fairly sharp on those chamfers, so I'm going to click OK on these, and it's going to generate our toolpath. That is our deburring. It has deburred all our edges except for inside these holes, which we're not going to be able to get with this tool, and this bottom edge. I do want to get this bottom edge, and we can get it with the tool. So we're just going to make another toolpath for a 2D contour. It's the same tool. I'll click on our edge, and then under passes, this chamfer width is again 15 thou. And the chamfer tip offset, let's do 0.24. And if I hover over this, it'll show how far. It'll show what that means. It's just like how far off the bottom we want. Since we want the side of the tool to be as close to the edge that we can get it, we're going to choose most of the way down the tool. I think 0.23 is actually better. And then we can see that we've also made our chamfer here, and it looks fairly good. This looks like it's going to work. Let's watch this. Just these two. Just our deburr, and then hopefully this will mean we are done with the cam for the first side of our part. And that looks correct. And then the final thing that I'm going to do is I'm going to simulate everything and just make sure there's nothing crashing. So we're going to watch this very quickly. I'm going to turn on the fixture, and then let's go fairly fast and make sure nothing looks terrible. Alrighty, that looks great to me. And then one last thing, before we post-process our operation and make sure that we can send it to the machine, we're going to want to select which machine we have. To do this, we go under Machine, click Select, and then in Cloud, we're going to have all our Bechtel machines. For some reason, there's two VF2s. We're going to click on the one with the Bechtel milling post, select this, hit OK, and then looks good. And now we're ready to post-process and send this on our way. All right. Thank you. That is it for the first operation of this part, and I'll come back to you with another video for making soft jaws and then the second operation.